Welcome back, students. In this video segment, we will talk about section 13.3, arc length and curvature. Before we get started, though, I want to give a really brief recap of a couple of items, really important items from section 13.2. The reason being is we're going to be using these items to do some of our work tonight or today. So consider from 13.2, consider a space curve and consider the position vector r of t pictured here. So suppose this is the position vector at some time t, and then here is the position vector at some time t plus a small increment in time. So let's say this is r of t plus, in 13.2 we said r of t plus h, but I want to use the delta notation for a small increment in time for our section. So the second position vector is the position vector at some time t plus a little increment, delta t. Okay, let's find a vector from the tip of r of t to the tip of r of t plus delta t. Let's in other words draw the displacement vector between the tip of the two vectors. So here is the displacement vector, and I'm going to label that displacement vector using that same delta notation. The delta essentially means change in, so the small change in r, position vector r, corresponding to a small change in time. Okay, and I stopped the video for a second just so I could squeeze in some more room above. That small change in a position vector, delta r, by our work really early on in the course, finding the distance or the displacement vector between two vectors, is nothing more than the position vector at t plus delta t, so it's r of t plus delta t minus r of t. Okay, now the idea in the last section was to let delta t approach 0 so that we could identify what we call as the tangent vector to the curve at the tip of r of t. Well, the problem with that was that as delta t, which used to be h, was h in section 12 and 13.2, as h or delta t approaches 0, delta r approaches 0, leaving us with a vector of no length. So what we did is we took delta r and multiplied it by the reciprocal of the small change in time. Since the small change in time is a small number, you can think about it as a fraction, multiplying by the reciprocal then is multiplying by something more than 1, and that tends to stretch the vector's length out. So this new vector, which didn't turn out real well here, so let me try this again. This new vector, I'll give you a chance to use a different color too. Let's say in green. This new vector we get by taking delta r and multiplying it by the reciprocal of delta t, stretching the vector delta r out. Okay, so then what we did is we let delta t approach 0, and at least geometrically it seems reasonable that green vector should approach the tangent position. Since delta t is approaching 0, r of t plus delta t is going to be approaching reasonably r of t, so that means that the net result as delta t approaches 0 should be that we approach the desired tangent position. So that red vector is the result of taking the limit as delta t, h in the previous section, of this delta t approaches 0 of this difference quotient, r of t plus delta t minus r of t over delta t. And we define that as being the tangent vector to the function. And we define that symbolically as the derivative of the position vector r of t. So r prime of t is a vector that is tangent to the curve. So it's tangent to the curve, and also points in the direction of increasing t. Points in direction of increasing t. And essentially what that means is that the tangent vector points in the direction in which the curve is oriented. Remember, curves given in parametric form ultimately as vector functions have a direction in addition to an actual curve. Okay, and the really good interpretation is that we have an object moving along that curve. So r prime of t is tangent to the curve, tangent to the trajectory of the object, and points in the direction the object is moving. The last thing, or one of the last things we did in that last section, was to take r prime of t and divide by its own length, forming a unit vector, which we call t of capital T of t, if you will, that equals r prime of t multiplied by the reciprocal of the length of r prime of t. And symbolically, we can write r prime of t over the length of r prime of t. So this is a unit tangent vector. Okay, also pointing in the direction of increasing t. So that brings us to our section, the section, our current section. We're still considering a space curve. Where space curves are given as position vectors. We're still given a space curve, and our first interest in this section is to find the arc length of the curve between two given position vectors. So we have a position vector, let's say r at time equals a, and another position vector r at some time later at r of b. And our first goal, is to find the arc length, find the length of the curve, or the arc length, the length of the curve between r of a and r of b. Okay. Now I do this a little bit differently, actually a lot differently than a lot of textbooks. I use an explanation that's very common in physics. So if my explanation looks different than the text, it's on purpose. This is supposed to be this course is a course primarily for STEM majors, STEM field majors, and specifically a lot of engineers take this course, and engineers need to take physics, so I try to tailor my lectures toward what students of physics will be saying, or are saying if they're taking the course concurrently. So here's the idea. The idea is to break up the arc from time equals a to time equals b into an infinite number of small arc lengths, little sub-arcs, and find the length of that sub-arc, that little tiny arc length, that little piece, and then add them up. Okay, so if you miss what I just said, it's no big deal. I'm going to draw what's going on here. So here's the curve, let's say at t equals a, and here's the curve at t equals b. The idea is to imagine slicing up the curve into an infinite number of little arc lengths. I'm trying to draw them in here. Infinite number of small changes in the arc of the curve. Okay, each of those little changes in arc length we can refer to as symbolically ds. Okay, ds rather than delta s. The reason we use ds is that ds is technically it's called a differential of s, and for us we can interpret as meaning that we're looking at an infinitely small change in the curve, whereas delta s would be a infinitely small change in the curve. Infinitely small change in a curve, ds. Okay. I know this sounds funny to a lot of people, especially if you had calculus instructors who didn't present things using differential geometry the way physicists like to do things. But it works out really well. So the idea is to break the arc length, and let's call the arc length L. So L is the length of the arc that we're after. The idea is to break L into an infinite number of small, and how small, we mean infinitely small arc lengths, and then sum them up. Okay. So if we were using the non-differential notation, if we were using delta s for a very small change in arc length, but not infinitely small, we would sum up those small bits of arc lengths by using sigma notation. Okay. Now what we're doing though is we're imagining we're slicing the arc L, or the curve, the arc length L, into infinitely small bits of arc length ds. So we're going to do that, and then we're going to sum those up. We sum up an infinitely small objects, or infinitely small changes, by using integration. Okay, so the total arc length then will be the integral, or you can think about informally the sum of the small ds's, all the little ds's, as time ranges between a and b. Okay, so let's develop a formula for this arc length. Let's develop a nice little formula for this arc length. So here is, once again, here's the curve, and let's take a look at again a small portion of the curve captured off between two position vectors, one at time t and one at time t plus delta t, where delta t isn't infinitely small, it's just some small change in time. Okay, now what we started out with in this lecture with the recap was the small change in the position vector, not in the arc length, but in the position vector. Small change in the position vector. The length of that small change in the position vector is approximately equal to the corresponding change in the arc length, but you can tell from my drawing here that it's not equal. It's in fact, with my curve, that the length of delta r is smaller than that desired delta s, the desired arc change in the arc length. Okay, so kind of backpedaling here, delta s is the length of the arc of the curve between the two position vectors. So we're letting delta s equal the length of the curve, the length of the curve between, and very often we call that portion of the curve the arc, the length of the curve between the position vectors, r of t and r of t plus a little time later. Okay, so from the drawing, it's pretty clear that that small arc length then is approximately equal to the length of delta r. Not equal, obviously. Again, delta s appears in my drawing to be longer. I'm going to rewrite the length of delta r by dividing by and multiplying by delta t. Okay. I'm going to extend the length bar from delta r to include delta t. Delta t is just a scalar, so we can bring that into the length bars, if you will. Okay, so as delta t approaches 0, this approximation becomes exact. Let me say that again. As delta t, the small increment in time from t to t plus delta t, as that increment in time shrinks smaller and smaller and smaller, that little delta r should get smaller and smaller and smaller. And the smaller delta r gets, the better it approximates in magnitude the delta s. So it seems reasonable to say that as delta t approaches 0, the approximation becomes exact. The approximation becomes exact. Exact. Okay. So as delta t approaches 0, though, all of our deltas then can be replaced with d's to indicate infinitely small. So the differential of s, the infinitely small change in the arc length, then is equal to the length of, well, as delta t approaches 0, dr dt approaches, I'm sorry, delta r over delta t approaches the derivative dr over dt times dt. So this is our formula for the infinitely small arc length that we're adding up by integration. Okay, notice that the squiggly equal sign, the approximate equal sign, became an actual equal sign, and that's again because as delta t approaches 0, the approximation that delta s is approximately the length of delta r becomes exact. Okay, so our formula for arc length then takes on a whole new look. The formula for arc length, which was pretty sweet and small, is time goes from a to b, t goes from a to b of ds, the sum of all the little ds's then, becomes the integral from a to b. Now that little ds, to use using the different notation, the prime notation for derivatives, can be written as the length of r prime of t dt. So the length becomes the integral of the magnitude of r prime of t. Oops, let me clean that up a little bit. R prime of t with respect to t. Okay, so this is our workable formula. This is a formula that we can actually use to find arc length. Okay, so if specifically r of t equals the vector whose components are given by component functions x of t, y of t, and z of t, then r prime, obviously, and I'm going to remove the of t's. I'm just going to write the variables x, y, and z. So x prime, y prime, and z prime. So our formula for arc length becomes finally the integral from a to b. The length of r prime then is the square root of x prime squared plus y prime squared plus z prime squared, integration with respect to time. Okay, and this is a really famous formula for the length of the space curve. Notice that the length of the space curve can either be given as in scalar form, as that I squared off in red there, or as I'll square off in, let's say, green. If I can do that quickly, yeah. Can given in vector form also. Okay. Okay. Well, let's do an example. Let's do an example. Let's find the length of a helix. Let's find the length of a helix would be infinite. Let's find the length of a piece of a helix. Okay, so that's going to be our first example here. So example. Let's see here. Find the length. Find the length. And I think I'll pause the video to write out the rest of the problem. See you in a second. So here's our problem. Find the length of the portion of the helix given by x equals cosine of t, y equals sine of t, and z equals some constant ct from t equals 0 to 2 pi. Now, if you don't remember about the helix, or if you don't recall the discussion about the helix, you might want to pause the video, go back to the first video, or the video in the last section, I think it was the last section, where we talked about a vector function giving us the helix. Or you can just go forward and maybe review it later. In any case, I want a length of a part of a helix from t equals 0 to t equals 2 pi. So what I did is I drew the helix for us again. Okay, and so the helix is in red. The black arrows are indicating the direction of the curve. And essentially what I'm interested in is the length of sort of one revolution, if you will, of this helix. Okay, one revolution. Now, I want you to concentrate on the formula for the helix just briefly, because I'd like to pose a question before we actually do this. Here are the parametric equations for the helix. Again, x equals cosine t, y equals sine of t. Remember, x and y given parametrically by cosine t and sine t. They give you a circle, so the x and y stay on a unit circle. The z value equals ct, and we analyzed the z value of a helix similar to this in a previous video. This c can be thought of as the rate of increase of z. The time derivative of z, dz dt, is equal to that constant. So that c is a measure of how fast the z value is increasing. So if c is very small, then we have a sort of smashed helix, a low helix. So if c were small, we'd be looking at something like this. If c is large, then that stretches out the helix. Okay, so again, dz dt is telling you that c is increasing at a constant, that z is increasing at a constant rate of c. So again, if c is small, then z will the altitude, the height of this curve will increase slowly. If c is big, then we start wrapping around the curve in a sort of elongated ellipse. Okay. So the reason I did this little analysis with c is when I do in-class lectures on this, I like to pose a couple of questions before I do this problem. First question is, what do we expect the length of this red helix between t equals 0 and t equals 2 pi? What do we expect it to be more than? What do we expect it to be more than? So here's your hint. If c were actually equal to 0, then z would equal 0, and we'd travel going around and round and round and round a circle, the unit circle. Then the length of the unit circle would be 2 pi. 2 pi r, 2 pi times 1, which is 2 pi. Okay, well, c is not necessarily 0, so we expect the arc length to be greater than how much? We expect it to be greater than 2 pi. Remember, c is a measure of how stretched out or how compressed this helix is. If we stretch the helix out, our length is going to be substantially more than the length of the circle that's projected from the helix into the xy plane, which would be 2 pi. Okay. Now, you don't need to completely understand that analysis to find the arc length. In fact, you don't have to understand the analysis at all, but I'd like you to. It's kind of an important thing to be able to analyze these curves. So the length equals the integral as t goes from 0 to 2 pi of the square root of x prime squared plus y prime squared plus z prime squared, integration occurring with respect to t. Okay, so let's just continue on with this. So our length then is the integral from 0 to 2 pi of the square root of, well, if x equals cosine of t, dx dt is, oops, negative sign. Derivative cosine is negative sign. Derivative sine is cosine. So plus cosine squared. Derivative of ct with respect to c, we already have that up there, is c. So this is our integral. Now there's a reason why we had you take Calc 2 before you take Calc 3. Calc 2 you study two things. You study integration techniques and series, basically those two things. So some of these arc length formulas require integration techniques beyond Calculus 1. This one doesn't. This one won't. All it requires is the most important identity from trig to make the integrand simpler. Sine squared t plus cosine squared t is how much? You said it. I'm a mind reader. No, I have a lot of faith in your ability to remember the trig, especially if you got through Calc 2 with all that trig. In any case, we're integrating the square root of 1 plus c squared dt. Now there's no difficulty in this integral. C is a constant. C is constant. It's not a non-constant function of t. So there's no fancy integration required here. The integral of a constant with respect to t is just t times that constant. So this is t times 1 plus the square root of 1 plus c squared as t varies from 0 to 2 pi. So the result is 2 pi times the square root of 1 plus c squared. Back to my question. What do I expect the length to be more than? I expect it to be more than 2 pi. And it's pretty clear that this is. 1 plus c squared is more than 1. So if I take something more than 1 and take its square root, I still have something more than 1. And 2 pi times something more than 1 is greater than 2 pi. And notice that as c approaches 0, what does the length approach? Notice we have what we would expect. As c is allowed to approach 0, the length approaches 2 pi, which is what we would expect to happen. We would expect to have the length of the helix approaching the length of the circle that's projected into the xy plane. Okay. Okay, now before we get into the next really major item in this section, namely curvature, I'd like to finish our discussion of arc length with a situation that occurs not too often, but often enough so that we might want to consider it. So what am I talking about? Suppose I would like to find arc length or use arc length as a parameter. Now, that sounds pretty bizarre at first. So here's a space curve. And here's r as a function. Here, let's just say here's r as a position vector. Let me clean up my arrow there a little bit. Here's r, a position vector r. I would like to write r, here's a different one, a different position vector, as a function of how far, let's say that initial position vector is r sub 0. I'd like to find r as a function of how far I've traveled along the curve. If that still sounds funny, I don't blame you. I would like to write r as a function of arc length. So if, and I see if I can do this, if the green arc length here is known S, I would like to be able to find this red position vector as a function of how far I've traveled along the curve. So in other words, if somebody tells me I have traveled 15 miles, I would like to be able to then compute the position of the person after having traveled 15 miles. If someone says I've traveled 20 miles along the curve, I would like to be able to compute r, the position vector of 20, where 20 is not time, but 20 is the arc length along the curve. Okay, so let's do an example that kind of illustrates this idea. So for example, so here's the example. Reparameterize the curve, a helix. Reparameterize the curve r equals the vector function whose components are 3 cosine t, 3 sine t, and 4t, using arc length as a parameter. So I drew a representation of the helix in red. In red is the actual curve, and s is a given arc length along the curve. So if I specify a given arc length along the curve, I would like to be able to find immediately a position vector. Oops, let me see if I can make it better. A position vector to where I end up on the curve. I would like the position r as a function of s, not as a function of time. Okay, so the first thing we're going to do is going to be to find s as a function of time, the arc length as a function of time, the arc length as a function of time. This is referred to in your text as an arc length function. If you missed what I just said, the length of an arc is the integral from a to b of the length of r prime dt. Okay, and that gives you the length of the curve from time equals a to time equals b. Okay, what I want to do is I want to find a function, an arc length function, which gives me the length of the curve between time equals a, and watch this on the little curve that I've written down below, time equals a and time equals t, where t is variable. So I want to leave the upper limit of integration as variable. So I'm going to have an arc length function L, which is the integral from a to t of the length of r prime dt. So that will give me arc length s as a function of t, and this is often referred to as an arc length function. Arc length function. Okay, so let's do that for our helix. I want the length of the curve s as a function of time. Well, our time, we need to start somewhere, and you can start the time a in the integral at any place you want. In particular, though, we're going to start when time equals 0. So our arc length formula is going to look like the integral from 0 to t of the length of r prime dt. Now the author of your textbook did something really good, and he changes the variable of integration from t to u, so that our upper limit of integration and the variable of integration are different. The author of your textbook replaces the variable t with the variable u of integration, which is technically what we really need to do, so that our upper limit and the variable of integration are different. And if you'll recall, the variable of integration in a definite integral has no effect on the value of the integral. The variable of integration in a definite integral is often referred to as a dummy variable. It has no effect on the value of the integral. I tend to leave, and this is not the best habit, but I tend to leave the t in the formula and just write the formula as you see it written here. Okay, and I won't mark you off if you don't change your variable from t to u. But technically, it's probably a good idea. Okay, but it's one that I think is forgivable here. So this is the integral from 0 to t of the square root of dx dt, or if you use your author's correct version, dx du squared. So 3 cosine t or 3 cosine u, the derivative would be negative 3 sine t or u. So I'm going to leave t's in there. So negative 3 sine t, it's dx dt squared, plus dy dt squared, 3 cosine of t squared, plus dz dt, derivative of 4t is 4. This looks very much like the integral we evaluated in our last example. So this is the integral from 0 to t. Sine squared plus cosine squared is 1. So 3 sine squared plus 3 cosine squared is the quantity 3 sine squared t plus the quantity 3 cosine squared t is 9. We have 9 sine squared plus 9 cosine squared is 9. So 9 plus 4 integrated with respect to t. So this is the square root of 13 integrated with respect to t. So this is nothing more than t times the square root of 13 from 0 to t. And this is where it's kind of a good idea to have your variable of integration something else other than t, but I'll let it go here. So this is t times the square root of 13. So the arc length s equals t times the square root of 13. Now I want you to see our arc length formula. I'm sorry, our position vector formula, our vector function formula that we started with. It looked like the vector whose components are 3 cosine t, 3 sine t, and 4t. And the idea, go back right to the beginning, was if I specify, look at the drawing, if I specify an arc length s, I would like to find the blue position function that tells me where I am, r of that s. And I can do that now. Since s equals t times the square root of 13, I can solve for s, and that gives, t rather, and that gives me t equals s over, you know what? I think I made a mistake, and I think you probably caught it, because it's a pretty obvious mistake. I'm going to fix that right now. So let's, before I continue with that line, let me get rid of that line. Did you catch it? It's the arc length is the integral of, now here's the line we should focus on for my mistake. I'm not going to edit this out. I think I should keep this real, including my mistakes. So on this line there's a mistake. Z equals 4t. So dz dt equals 4. And the arc length is the integral of the square root of dx dt squared plus dy dt squared plus dz dt 4 squared. 4 squared is not 4, it's 16. So I'm going to correct that on the next line. So it should be 16, 9 plus 16, which is kind of cool. I get a little reward for correcting my mistake. 9 plus 16 is 25. And then the integral of the square root of 25 is obviously 5, so the integral is 5t. And finally, arc length, my arc length function then is s equals 5t. Sorry about that. So if I solve that arc length function for t, I get t equals s over 5. Now I'm going to take t and equals s over 5 and put that back into my position function. So that will give me r as a function of s equals, the vector whose components are 3 times cosine of s over 5, 3 times the sine of s over 5, and 4 times s over 5, so 4/5 s. And now I'm able to find the position function as a function of arc length. Okay, so let's move on to our next the next of the two main topics for the section, arc length. If I were teaching this as an in-class lecture, I would suggest a break at this point. So if you'd like, stop the video and take a break. Otherwise, power through it. I'm going to go take a break. I'll see you in about through video magic. I'll see you in about a second. Okay, I'm back from the break. Okay, our next topic is a big one. It's called curvature. Curvature. Without taking any calculus course, you probably have a pretty good idea of what curvature should do, what it should measure. I've drawn 3 curves, and I've drawn a point P on each curve. Which curve has the most curvature at the point P? Just think about that to yourself and answer. Don't think about it too long, just answer it very quickly. The first, the second, or the third. Which one has the most curvature at the point P? And if you said the first curve, you have a nice, powerful intuition of what curvature should measure. Curvature is a measure of how quickly a curve is changing direction, how fast it's bending. How quickly a curve is bending as we move from point to point. But I want to put curvature in a context of the quantities we've been dealing with so far, namely the unit tangent vector. So what am I talking about here? So I'm going to use green to draw a unit tangent vector at the point P on the first curve. So here's the unit tangent vector. So this is a tangent vector of length 1. Now if I move along the curve P just even the slightest amount, then the unit tangent vector will make a big swing. If I just move just the smallest amount of distance along the curve, the unit tangent vector doesn't change its length. It has length 1, but it makes a pretty big swing. Okay? Whereas if I'm at a point P on the second curve, here's the unit tangent vector, and then if I move a little ways along the curve, the unit tangent vector doesn't make too much of a change. And along the third curve, which looks like it's a line, if I draw a unit tangent vector at a particular point P, and then draw another unit tangent vector after moving along the curve just a little bit, there's no change in the unit tangent vector. So besides measuring how quickly a curve is bending or changing direction, I can think about defining curvature as how fast the unit tangent vector t changes for a small change in arc length. That means as we move along the curve a small distance. Okay, and that's exactly how I'm going to think about curvature. And it's also going to be how I'm going to get a formula for curvature that we're going to be able to deal with. So curvature should measure how quickly a curve is changing direction at a particular point. That's our sort of intuitive idea of how fast it's bending at a particular point. And I'd like it to answer the question, how fast is the unit tangent vector t changing for a small change in arc length along the curve? So let's analyze this idea some more. Okay, so I'm going to draw 3 curves, or consider 3 curves. Here's one curve, first curve with what we understand right now as having not so much curvature. This curve doesn't bend very much. So here's that green unit tangent vector at the point. Now let's assume that I move a small distance along the curve. So I move from the first point to the second point through a small, infinitely small arc length ds. And my new tangent vector looks like unit tangent vector just turned a little bit, just bent downward a little bit. So here's my new tangent vector, unit tangent vector. It's the strangest looking T I've made today. Now every T I draw is going to be weird looking. Okay, there, that's not so bad. Let's take those two unit tangent vectors and put them tail to tail. If I take the first one and the second one, put them tail to tail, okay, then I get a small change in the unit tangent vector, which I'll denote as d capital T, small displacement vector. And you notice that the length of dt is small. It's the small change in the unit tangent vector amounts to a small dt. So dt is a small vector. So dt divided by ds, the small change in the tangent vector divided by the scalar, or multiplied by the scalar 1 over ds, is then going to be, and you'll forgive my notation here, it's a small quantity, but it's a small vector. Okay, and then we notice that this corresponds to a very slight bending in the curve, slight bending in the curve. Okay, now let's look at the extreme. Here's our new curve. Here's our new curve, and we're going to start, say, at this point, and we'll consider the same arc length ds. So the arc length is ds, is this little piece of change in the arc length, and here are our unit tangent vectors. Here's our unit tangent vector, length 1, length 1, length 1, length 1, length 1. And here's our unit tangent vector now. Still length 1. But now look what happens when I put them tail to tail. Here's the first one. Here's the second one. And I've drawn it a little bit too long, I think. Yeah, I should keep it not so long. Here's our second one. They should have exactly the same length. They're just unit vectors. So this vector from tail to tip to tip, that's an ugly vector. I think I'm drinking too much coffee. This vector is dt, the change in displacement of the two tips. So now dt over ds is dt is a much bigger displacement vector than before. Divided by ds, that is a large vector. And this indicates sort of sharply bending, a lot of curvature, a lot of this thing we want to call curvature. So here's our last extreme, straight line. Here's at the first point, t, unit tangent, length 1. And then from that first point, we're going to move a small arc length ds and draw another vector. Another unit vector, of course, length 1. Now draw them tail to tail. There's the first one. And right on top of that one, just for emphasis, here's the second one, which I'll now change to, just so we can actually see it. Well, maybe I'll change it to orange. So here's our second one, placed right on top. Okay, so that's also our second vector. So what is dt? It's the zero vector. There is no change. There is no change in the vector. Okay, so dt ds, dividing by ds, is the zero vector multiplied by 1 over ds, or divided by ds if you want to think about that. It's 0. There's no bending, no curvature, no bending. No bending whatsoever. So this vector, the derivative of t with respect to arc length, is something that we're going to use to actually define curvature mathematically. It seems to work pretty well for defining curvature, except for one thing, and what is that? dt ds is a vector, and curvature is a scalar quantity. Curvature doesn't have direction. It just measures how fast the curve is bending at a point. So how are we going to define curvature? Well, I kind of just gave it away. Definition of curvature. Curvature. The definition of curvature is it's the length of dt ds. dt ds gave us a vector which really nicely described curvature, except it gave us a vector every time, a large vector, a small vector, or the zero vector. Take the length of that vector, we have something called curvature. Now, for curvature, the symbol kappa, the Greek letter kappa, which I can't really distinguish too much in my writing between the kappa and the small k. In fact, I think the Greek letter kappa morphed into our k. Kappa, small Greek letter kappa, if you call it k, and nobody's gonna scream at you. The Greek letter kappa is reserved for, in our textbook, curvature. So the curvature is kappa equals the magnitude of dt ds. Okay. Now, there's a problem with this. It's the magnitude of the derivative of your tangent vector with respect to arc length s. But what is our tangent vector very often a function of? Our tangent vector, unit tangent vector, remember our unit tangent vector is, from our last section, it's the position vector divided by its length. But the position vector is most often given as a function of time. So the unit tangent vector is very often given as a function of time, and we're looking at the derivative of the unit tangent vector with respect to arc length. So to be able to really use the definition effectively, quickly, or efficiently, we would have to have our arc length, our unit tangent function as a function of s. We would need this, t, our unit tangent, as a function of s. Now, that means we would have to replace t with arc length, find the arc length function as we did in the last example, or an example in the last hour. And that's not necessarily very easy to do. If you miss this, here's the bottom line. This formula works well for t as a function of arc length. We would like a formula, a curvature formula, which works when our arc length, our tangent function t is a function of time, small t. Okay, well, we can get that without too much problems, without too much of a problem. So I'm going to drive that for you. I'm going to drive a new formula for curvature. We'll have several formulas by the end of the lecture, but I'm going to drive a new formula for curvature that gives curvature in terms of time and not arc length. Okay, so notice that dt ds can be written as, using the chain rule, dt d time times d time ds. Okay, or treating differentials like fractions, dt d time over ds d time Okay, so my curvature then, kappa, equals the length of dt ds is then equal to the length of dt d time, d capital T d time, over ds d time. Okay, or dt d time. ds d time is the rate at which arc length changes. That's always positive. If you're not sure about that, that's okay. This is divided, oops, this is, you can think about it if you, oh, sorry. This is ds dt. Now, remember that ds dt is equal to the magnitude of r prime. Okay, from the beginning of our discussion. So that kind of shows you that we don't really need the absolute value bars above on the ds dt. But it does give us our workable formula. Curvature is equal to the length of the derivative of t with respect to time. That's what we have on the numerator, divided by the length of r prime. And this is a very popular formula for curvature. This formula is good when t is a function of time, okay, which it most often is. The first definition, or rather not the first definition, the only definition, is a good formula if t is a function of s, which is not usually the case. Okay, very often it's the case that t is a function of time. So this is really our first workable or popular formula for curvature. It is the length of t prime over the length of r prime. Looks like a v prime in the denominator. This is an r. Okay, let's get away from some theory and look at a specific example. What do we expect for the curvature of a circle of radius a? Again, what do we expect for the curvature of a circle of radius a? What would you expect to? What would you expect of it? Would you expect a small what would you expect of a circle with a small radius? Would it have big curvature or small curvature? We have big curvature. The unit tangent vector on a small circle bends very, very quickly. On the other hand, what about a big circle, a large circle, like one the size of the Earth? For a circle the size of the Earth, the unit tangent vector on the circle, let's say a tangent vector of length 1 foot as you move along the Earth, it hardly bends at all. We don't perceive any curvature at all as we walk along the Earth. We feel like we're walking along a straight line. So big circles should have small curvature, and the smaller the circle, we should have big curvature. And should the curvature of the circle vary depending on the point you are on the circle? No, the circle seems to have the same amount of bending no matter where you are on the circle. So we would expect the curvature of a circle to be constant for one thing, not change from point to point. And the larger the radius, the smaller the curvature. The smaller the radius, the larger the curvature. So if you didn't see what I'm talking about, here's a few circles. On the first circle, remember the curvature measures how fast the unit tangent vector is changing. There's a huge change as I move a small distance along the small circle. But on the big circle, the unit tangent vector is here, and a little while later, same arc length as before on the small circle. It's almost linear. Circles with large radius become more and more linear the bigger r is. So we expect the bigger the radius of the circle, the smaller the curvature, and vice versa. The smaller the radius of the circle, the bigger the curvature. What is the simplest function that does that? If I want curvature to be a function of the radius, if I want curvature, and the radius is, say, a, radius is a, what would be the dream function, the dream curvature? Dream curvature function. Curvature function. If you had to come up with one, curvature would be equal to what? Bigger the radius, smaller the curvature. Smaller the curvature, bigger the radius. It would be nice if our curvature was the simplest function that behaves the way I've described curvature of a circle, and it would be 1 over the radius of the curvature. If the radius is big, curvature is small. The radius is small, curvature is big. As the radius approaches infinity, the curvature approaches 0. As the radius of the circle becomes infinite, on the surface of the circle, it appears that it's linear. Okay, so let's see what the actual result is. Let's actually find the curvature of a circle of radius a. Find the curvature of a circle of radius a. Okay. Well, in order to do that, we need to parameterize the circle of radius a. So we can write a vector function for the circle of radius a. Now remember, the curvature depends on the derivatives of the unit tangent vector and the unit unit tangent vector and r prime. So we need a vector function for r. So let's parameterize the circle of radius a. Easy. The simplest way to parameterize the unit circle is x equals cosine of t, y equals sine t. So how do I stretch the unit circle into having a radius a? Multiply each of the component functions by a. So that gives us a position function for the circle of the vector function whose components are a cosine of t and a sine of t. So there you're looking at the vector function, a vector function for the circle of radius a. Now keep in mind that curvature is the length of the derivative of your unit tangent function divided by the length of the derivative of your position function. Okay, so we need two vectors. We need the unit tangent function and its derivative, and the position function and its derivative. Well, we have the position function. So the derivative of the position function is negative a. It's the vector whose components are negative a sine t and a cosine t. So r prime is the vector function whose components are negative a sine t and negative a cosine t. Okay, so what is the unit tangent vector? The unit tangent vector is r prime over the length of r prime. By now that should be familiar to you. It was in the last section. So this is negative a sine t, a cosine t, divided by the length of the same vector, divided by the length of that same vector. What's the length of the vector negative a sine t, vector whose components are negative a sine t and a cosine t? Well, since sine squared or cosine t, sine squared plus cosine squared is 1, we're looking at negative a, vector whose components are negative a sine t and a cosine t, divided by a. So my unit tangent vector takes on the appearance of negative sine t cosine t. Okay, now that's the unit tangent vector. The curvature requires the derivative of the unit tangent vector. So t prime equals derivative of negative a sine is negative, of negative sine is negative cosine, and the derivative of the second component is negative sine t. So there's the derivative that goes in the numerator inside the magnitude of my curvature. I also need r prime, okay, which I already found. So my curvature is then, again, it's the length of t, oops, I put a double prime in there. It's the length of t prime over the length of r prime. The length of t prime, what's the length of the vector whose components are negative cosine t and sine t? The 1. Okay. What's the length of r prime? Well, there's r prime. What's the length that we've kind of figured it out when we found the unit tangent vector? The length of r prime is a. There we go. The curvature of a circle of radius a is 1 over a. That's pretty nice. The reason why I think it's pretty nice is because it behaves exactly the way we expect the curvature of a circle to behave for either small or large values of a, and it's simple. Okay. Well, we're almost done with the section, but we have a couple things to do. Okay. First, some formulas for curvature. These are in your textbook. Curvature. Popular formulas for curvature. First, the definition. Definition of curvature. Okay, so this is good, once again, if t is a function of arc length, which it almost never is. We also have the one we just developed, length of t prime over length of r prime, and this is good. Oh God, oh my goodness. Sorry about that. Good if t is a function of time. Okay. There are others. There's this popular formula. It's the length of r prime cross r double prime over the length of r prime cubed. Okay, and this is good to avoid tangent as a function of time. It only involves our position vector r and its derivatives and its second derivative. Okay. See proof, by the way, in text. I want you to look at that proof. Okay. I wrote in my book, or in my notes, that it's on page 880. Oh no, that's the 7th edition. We're looking at the 8th edition. And I don't have my book right in front of me. It's in a section. Okay. There's one more formula, and it looks like the absolute value of the f double prime over 1 plus f prime squared all to the 3/2 power. And this is good if your curve is given as y as a function of x. If you're given your curve as a function of x and not as a position, in terms of a position function or a vector function, then this is a good alternative. Okay. See proof in text again. Text. See proof in text. I would like you to look at that proof. See proof in text. Yeah, I think studying the proof would be good for you. Okay. All right. Well, we're almost done, but we have a little work to do. We're almost done, but we have a little bit of work to do to develop our last concept that kind of also involves curvature. To end, I would like to consider this physical situation. Okay? And we can make it kind of fun if we can call it fun. Imagine that we're in a spaceship. Okay, at the origin, let's say, is the Earth. So that's our reference point for this situation. So the Earth is at the origin in 3 space, and we're on some plane curve. I would like a way of describing the motion of the spaceship that I'm on that doesn't depend on using the position vectors from the Earth. Okay, I would like a way of kind of describing my motion by using my position locally in space. So here's what I mean. Here's the first octant in 3 space, and at the origin we have the planet Earth, and we are in space moving along some space curve in a spaceship. Okay, and I would like a way of describing my motion, sort of radioing back to Earth some information about my motion that'll help to completely describe my motion, but not depend too much on my distance of my position function from the Earth. So if you're not following, just maybe try to pick up and follow now. So suppose I'm at a point right here in space. I can use my unit tangent vector to help me describe my motion. So I can radio back to the Earth my unit tangent function, unit tangent vector. Now, is that enough to completely describe, or to describe well, my motion in space? The answer is no. If I radio back my unit tangent vector at a particular point in space to the Earth, that will only tell them the direction that I happen to be going at that one point. Will it indicate to the people on the Earth that I'm sharply bending, or whether I'm going in a straight line, or whether I'm turning but not so much? No, it's going to indicate just the direction that I'm going at that specific moment. It will not indicate any kind of direction in which I'm maybe turning at the moment. So I would like another vector to do that. I would like a vector that points, a unit vector that points toward the concave side of the curve. I would like a unit vector that will point in the direction that I'm turning my steering wheel on the spaceship, and I would like it to be perpendicular to my tangent vector. Okay, I'm going to call that vector n. N is a unit vector. So is my unit tangent vector. I would like one more vector. I would like a vector that might help describe if I'm as I'm going along this space curve, am I twisting? Is my spaceship twirling around and around and around as I move forward? Okay, sort of like a corkscrew type thing. Am I moving in a sort of corkscrew fashion as I move along this curve? Am I twirling around and round and round? There's a third vector I can form that would do that. There's a third vector that I could form, and that third vector would be perpendicular to the other two. a third vector that I could form, and I'm trying to pick a color, would be this yellow vector, a unit vector. I'm going to call that yellow vector B. As it changes, it describes, as it changes direction, it describes whether I'm twisting around and around as I'm moving along this curve. Sort of corkscrewing around as I was corkscrewing around. That didn't turn out so well as I'm moving along this curve. This little triad of vectors, forms like a little tiny reference frame that changes from point to point on the curve. It's like three little axes that change that twirl around and twist, but still are always mutually perpendicular, mutually orthogonal to one another as I move along the curve. It's called the TNB reference frame. And it moves along with me. So T points in the direction of increasing T. N points toward the concave side of the curve, and B is perpendicular to both T and N. Okay, so we know that T is called the unit tangent vector. We have a name for N. N is called the unit normal vector. And B is called the unit binormal vector. Okay. Now these quantities are not difficult to find. There are formulas for these, and we'll talk about those in a minute. But associated with the TNB reference frame are also a couple of planes in space that are changing as I move along the curve. The plane that's determined by B, the binormal, and N. Take a look at that plane. What would it look like? The plane that's determined by B and N would be this plane. And it's an important plane. It has a special name. It's called the normal plane. Is called the normal plane. And of course, it's only good at the specific instant of time that my spaceship is located right at that point on the curve. But it's called the normal plane. Okay. If you were trying to find the equation of the normal plane, what would you choose as its normal vector? Let me repeat that. If you were trying to find an equation of the normal plane, what would you choose as its normal vector? And if you look at the green plane, it looks like the tangent vector would be fine. You could use the tangent vector as its normal. Oops, I don't want to be in green. The unit tangent vector can be used as its normal vector. Remember, to find an equation of a plane, you need a point and a normal. But there's an easier vector. Easier, just use r prime. You see, the unit tangent vector is just a shrunken down version of r prime. Remember, it's r prime divided by its length. Yeah, I'm bringing this up to save you a little time on your homework, because you're going to be looking at normal planes and one other plane associated with the reference frame, TNB. So there's another plane that's associated with this triad TNB. It's the plane determined by T and N. I'll try to draw in our same drawing in, let's say, some other smart color. Oh, I don't know. Purple. We'll try and see what it looks like. T and N T and N, they form a plane also. They determine a plane. Purple's pretty nice looking. They form a plane. T and N, they form a plane. They determine a plane. That plane is a little more abstract in terms of what it represents. That plane is the plane that comes closest to confining the curve in 3 space in a 2-dimensional object. If I could find the best 2-dimensional plane, 2-dimensional, well, it's all our planes are 2D for us. If I could find the best 2D plane that would fit this 3D curve just at that moment, it would be the plane determined by T and N. That plane has a special name. The plane determined by T and N is called the osculating plane, not oscillating, osculating plane. It's called the osculating plane. To osculate, I had to look this up years ago, means to kiss. To kiss. Okay, so it's the plane that just barely kisses the 3-dimensional curve and places it almost in a 2-dimensional plane. It's the best plane, 2-dimensional plane to contain the 3-dimensional curve. It's called the osculating plane. What can be used as its normal? Its normal. B can be used as its normal, but it's not a good idea. B is going to be I haven't shown you formulas for finding N and B, but the formula for B, actually finding B is kind of rough. B can be used as the normal for the osculating plane, for this plane. But it's better to use a different normal, and we'll see that in a moment. Okay, so for finding the normal vector to the normal plane, use r prime. To finding the normal to the osculating plane, B would work, but there's a better one. In order to get the better one, though, we kind of need a formula for these vectors. Okay, well we have a formula for T. For T. T equals r prime over the length of r prime. Okay. N is equal to T prime over the length of T prime. That's kind of amazing. That's kind of amazing. That N is equal to T prime over the length of T prime. Okay. B is not going to be too difficult to get for us. Okay. Here's a curve. T. Here's N. Here's B. What do you suppose is the formula for B? B is orthogonal to both T and N. That gives it away. Is T cross N. Now, in two of those three formulas, N and B, I gave you no proof that the normal and the binormal vectors were unit vectors. I haven't proven that at all. Let's see, I guess I can do one of them. Here, I'll prove that the binormal vector has length 1. That's pretty easy. The length of the binormal vector is the length of t cross n, since binormal vector is t cross n. So it's the length of, using the formula for, alternate formula for length of cross product, it's length of t, length of n, times the sine of the angle between them. And what's the angle between t and n? It's 90 degrees. Well, t is a unit vector, n is a unit vector, sine of 90 is 1, so the unit binormal has length 1. Okay. Now, we'll finish this this lecture with a good normal vector for the osculating plane. Let's go back. The osculating plane. The osculating plane is the plane determined by t and n. So, as I mentioned a few minutes ago, a perfectly legitimate normal vector would be the binormal vector. The binormal vector is perpendicular to both t and n, so it would definitely work if you were trying to find the equation of the osculating plane. But let's take a closer look at the unit binormal vector. It's t cross n. It's t cross n. But t is r prime over the length of r prime. And n is t prime divided by the length of t prime. So, if I want a quicker formula for a normal vector for the osculating plane, a quicker formula for a normal vector to the osculating plane, look at the formula for the binormal. All we need for a vector, for a normal vector, is its direction. All we need is r prime. We don't need the length of r prime in the denominator. The length of r prime is just a scalar. It's not going to affect the direction. And t prime. We don't need the length of t prime because it's just a scalar. So a quicker formula for a normal would be to use r prime cross t prime. When you get to the part in our homework, or your homework, where you find the osculating plane and the normal plane, you might want to refer back to this portion of the lecture for these vectors. It'll make more sense when you get there. I'm not looking at specific examples of the TNB reference frame. There's one in your textbook, I think there's a real nice one in your textbook. I recommend that you look at that example before you dig into homework. But in an effort to make this lecture not go on too much longer, I'm gonna end the lecture now. And feel free to send me emails with questions about anything, including an example of the unit tangent, unit normal, and unit binormal vectors, if you would like. And as usual, I am absolutely looking forward to talking with you all again soon.